Hello everyone and welcome back to a new video in our Introduction to the Finite Element Method series, in which we're going to continue talking about Chapter 4 of the book A First Course in the Finite Element Method by Daryl and Logan. And in this video, we're going to be talking about something called internal hinges. Now, this is also called released moments in Autodesk Robot, and we're going to understand how things are done in the finite element method, as well as how things are done in softwares. For the software part, I will just give a small heads up at the end of the video, but for now, we are going to deal with the theory here. This video might not be that long, so well, sit back, relax, and enjoy the show. What is the effect of an internal hinge? Now, you might know from statics that if you have a structure and you apply an internal hinge here, then you immediately know that the internal moment at the hinge equals 0. Now, why is the internal moment at the hinge 0? The internal moment at the hinge is 0 because there is no rotation resistance. What do I mean by this? What's the deflection shape of this beam? If you have this beam, the deflection shape kind of looks like this, where you can see there is a continuity in the slope of the beam. However, if you have an internal hinge, then the deflection shape of the beam will kind of look like this under uniform distributed load. You have something like this. And you can see the clear discontinuity in the slope. Another example for internal hinges and frames. If you have a frame like this under uniform distributed load, your deflection shape should look something like this, where the angle is still 90 degrees between the column and the beam due to the continuity, or something we call the rigid connection. The same frame, if you have two internal hinges here, now first of all, that's unstable if you have pins in the bottom, but regardless, the same frame under distributed load would have only a deflection shape like this, and the beams would not bend. You can see a clear discontinuity because the angle changed from being 90 degrees to being 60 or something. In other words, a discontinuity in the slope would mean that there is a sudden change in the moment, which could be a zero moment location, like in an internal hinge, or a plastic moment location, like in a plastic hinge. Please notice that a hinge does not resist rotation, thus doesn't develop any internal moments. So in other words, the internal moment at the hinge equals 0. So that's basically a quick note on what an internal hinge in theory means. And if you want to develop the finite element equations that correspond to this is basically two beams connected by an internal hinge of lengths known. Of course, you have here element number 1, which is on the left side here. If you have an internal hinge, and if you say that you are going to consider the internal hinge on element number 1, then your M2 equals 0, but the slope at the second point is not 0. And if you want to consider element number 2 as having the internal hinge, the right side, then the moment at point 2 equals 0, and there is a slope. Now notice that there is a strange thing happening here. You can see that there is an error in the book of Daryl and Logan. I can justify the error, but I'm still surprised. Like, this should be phi 2 M2, and this should be phi 3 M3 to denote for the moments and thetas of node number 3. You can see him doing this just fine, but doing this incorrectly, like he's using F2 and F1 here, although it should be F2 and F3. Now, why is he doing this? My theory behind this, this numbering is that he calls this the starting node and this the ending node, and he calls the starting node 1 and the ending node 2. It's kind of strange. I am more a fan of calling this phi 2 M2 and this phi 3 M3 and this F3 and this F2 because it corresponds to node number 2 here and node number 3 here. So a strange oddity in the book, but well, I'm here to explain that. Okay, now how do I do this? How do I deal with this? Well, let me explain this to you. First of all, what is the stiffness matrix? The stiffness matrix, we know, or the equation of equilibrium on the local sense, is basically local forces equals the local stiffness matrix multiplied by the displacement vector. Now, what are the local forces? Let's say we take element 1. The local forces for element 1 are basically F1y, M1, F2y, and M2. Those are the local forces. Of course, here this is a 1. What is the stiffness matrix? The stiffness matrix is EI over L cube and all the 4x4 elements here, the numbers that you see here. We have explained this before in another video that I will be linking above. And what is the deflection here? The deflection here is basically the movement in Y, the rotation around point 1, the movement in Y in point 2, and the rotation around Y around the point 2. So those are my basically 4 degrees of freedom for a beam. Now suddenly there is some breaking up happening here. Look, we are talking about element number 1. Element number 1, this element number 1, has a hinge at node number 2 of that element, as you can see here. Now this node number 2 has an internal hinge. What are the things affected by the internal hinge? The things affected by the internal hinge are that M2 equals 0. So which part is responsible for M2 and which part is responsible for all the other things? You can see this M2 being 0, and you can see some colored boxes. Because the book goes full on mathematics on you, so I want to explain this to you. You can see that, well, M2 is called here F2. By F2 in the book, it's meant, the meaning of F2 in the book here is basically all the forces that correspond to the release directions. I mean, this can even be a vertical force, F2y. This can even be M1. And it can also be a combination, like assume you have a release where you release both shear and moment, then those two things would be F2. So F2 are all the forces that correspond to the release direction, which means all the forces that are equal to 0 here, that we know that are equal to 0 due to releasing. F1 is the rest of the forces. In that case, it's F1y, M1, and F2y. K11 is a 3x3 matrix corresponding to the 3 degrees of freedom. You can see this in red. K12 is a 3x1 matrix that basically mixes and merges F1 and F2, because you can see that those are at the rows of F1, but at the columns of F2. Similarly, those are also some mixing elements because those are in the rows of F2, but in the columns of F1. K22 is the stiffness corresponding to the release direction, purely. Similarly, you have degrees of freedom here and degrees of freedom here. So you can stop the video and pause the video to get used to those matrices. Once you're finished stopping this video and getting used to these matrices, full mathematics happen now. What is happening here? Well, from matrix calculations, we know that F1, this, equals K11 multiplied by D1 plus K12 multiplied by D2. This is how mathematics work. You multiply the first matrix by this, and you multiply this by this. This is how matrix multiplication goes. Similarly, F2 equals K21 multiplied by D1 and K22 multiplied by D2. Why am I doing this? I'm doing this cool stuff because I know for a fact at the moment that F2 is 0. This doesn't get immediately clear, but I know for a fact that F2, at least in this case now, is 0 because the forces that are being released, and by F2 remember, I mean any released loading. This could be a force in Y, this could be a moment around the second point, this could even be the force in Y at the first node. Like this F2 doesn't correspond to node number 2, it corresponds to the release directions. So please, like, it might be confusing, and it truly is, but I'm trying to explain this to you that at least for the purposes of this derivation, 1 means unreleased and 2 means released for the purposes of this derivation according to Dariel and Logan's book. So F2, because those are released, should be 0. It becomes really crazy and hard when you get to the plastic hinge domain because then F2 is not 0, but this is something advanced. F2 here is 0 because it's released. Now remember, this F1 equals K11 D1 plus K12 D2, and I can solve this for D2. I can solve this equation for D2 and then plug it back in here, and that's what's happening here. You can see D2 equals this stuff, which is basically the solution of this equation. Let me explain. If I take this equation in the red box, then I could say F2 minus K21 D1 equals K22 D2. Of course, to eliminate K22, I need to left multiply by its inverse, and that's what you see here. Left multiplication by the inverse, and this is basically this. So it's just mathematics here. Similarly, what about F1? Well, remember that now I can use D2 and plug it back into the F1 equation. And you can see this happening exactly here. So this is D2. I'm going to take D2 and put it in F1. So F1 equals K11 D1. I'm not doing this matrix stuff because I want to be simple now. Multiplied by K12, open big bracket, put this stuff inside. Okay, before I continue, I missed two brackets here, so I need to bracket those two things now. This is going to be really spicy now. So F1 equals K11 D1 plus. And now I need to multiply K12, K22 inverse into the bracket. So this is going to be K12, K22 inverse F2. This is basically those two things multiplied by F2 minus K12, K22 inverse K21 D1. And this term is basically those two guys multiplied by this. Are we finished? No, because you have D1 here and D1 here. So you can take them as common factor and say F1 equals K11 minus K12, K22 inverse, K21, all of this multiplied by D1 plus this stuff. And you can see this happening exactly here. Notice that this is 0. So in most cases, this will be eliminated. In most cases. But this is basically a new stiffness matrix. You can see that this can be translated, at least this part, can be translated into becoming a new stiffness matrix. And now this is where MATLAB and your mathematics skills comes into play. Because from the initial matrix, you know what K11 and K12 and K21 and K22 is. You need to multiply that stuff to find some sort of cool new stiffness matrix. Lo and behold, you don't need to do this. That's your stiffness matrix. If you multiply those three things together to get the condensed, as they call it, the condensed stiffness matrix, you get this stiffness matrix. And multiplying all this stuff together gives you the stiffness matrix. The stiffness matrix connects V1, Phi1, V2 only. What about Phi2? It doesn't get connected. Why? Because it got condensed out. We have extracted it. All those calculations were performed to extract D2. Look, there is no D2 here, and D2 in our case was Phi2. Okay, but I still need Phi2 because of the calculations, right? You need to find the stiffness matrix. If you need Phi2, well, all you need to do is to apply some zeros here and some zeros here because it's not considered. This is the stiffness matrix of a released element in the rotation degree of freedom at node number 2. This can only be used, this stiffness matrix can only be used if you have an element and you're considering its far end to be released. If its near end is released, this stiffness matrix will not help you because then you would have to rewrite this full thing. Like this is totally different. Then you would have F1y being your F2 and M1, F2y and M2 being your F1 if you basically use or try to release, for example, the shear at the first element, first node. So this only works if you have release in the second node of the beam. And that's not how finite element method softwares, the commercial ones, do them. They do it differently, and I will be talking about the differences later. Okay, now let's apply that stuff into an example. So I have an example here. The question is, find the slope at node 2, the flexion and slope at node 3, and the hinge is at node 3. So he wants the slope at node 2, phi 2, and he wants the slope at node 3 and the deflection at node 3. Notice, at node 3, you have two slopes. You have the slope just from the left side, and you have another slope just from the right side, because remember, there is a discontinuity in the slope of this structure. There is a discontinuity due to the presence of an internal release or an internal hinge. So because of this continuity, you have phi 3 two times, and we need to calculate them both. At least the book doesn't do that, but I want to mention this very quickly before I continue. Okay, so how do we do this? Now, once again, I'm assuming that we are pros here. So of course, I'm gonna follow my finite element steps step by step. If you're not familiar with this, I will start linking up some multiple videos here that will help you try to understand the different aspects of finite element method as well as beams. Most of those are going to be my previous beam lectures where you can check out how you can basically assemble your stiffness matrix. Fine. Now to assemble my stiffness matrix local of 1 will actually equal the global. By the way, until now, all the local stiffness matrices were equal to the global stiffness matrices because in beams, the local direction and the global direction coincide. So the stiffness matrix of element number 1 is going to be a normal stiffness matrix. K2, on the other hand, is going to be a released or condensed stiffness matrix. So K2, the stiffness for element number 2, is going to have this crazy zeros in the fourth column and row. Why? Because there is a release. And K3 is going to be a normal stiffness matrix. And this is where things get crazy. Isn't element number 3 also released? Like, shouldn't I use for element number 2 a special K, and for element number 3 a special K? Because element number 3 is released in its beginning and element number 2 is released in its end. Shouldn't I use a special stiffness matrix for both? And the answer is no, you should not. This goes really deep in reasoning as to why, and I will talk about this deeper understanding later. So now I'm not really able to explain as to why you should only use one special matrix. Okay, so with that being said, let's take a look. Now we are pros. I'm not really taking too much time here because you know this so far. So this is element number 1, the regular stiffness matrix. This is element number 2, the special stiffness matrix with all the zeros. And that's element number 3, the regular stiffness matrix. Of course, here the L's are used because this is 2 meters. This is 1 and this is 1. So I can see the stiffness matrix being readied as we speak. Of course, what's the next step? Well, stiffness matrix assemble, right? So because you want to stiffness matrix assemble them, once again, I am saving your time because you've done this a million times. And this is the global stiffness matrix assembled. You can see the different influence domains. You can see the influence of element number 1 being here. And you can see the influence of element number 2 being here in the dashed line. And you can see the influence of element number 3 being here. Of course, you can distinctly see the zeros from element number 2. You cannot see a 0 here because 0 plus 6 from element number 3. So I have my stiffness matrix. Can I solve? Of course. Now this becomes just a joke. You have to dash and slash. How do you solve this? Well, look. This is the stiffness matrix, right? Now you need to find the force matrix or the force vector. What's the force vector? I will make me a big vector like this. At 1, there is something called F1y, which I don't know, and M1, which I don't know, at support number 1. At node number 2, I have F2y, which I don't know, because it's their action, and I have a 0 for M2. These are the external forces. What about node number 3? At node number 3, I have no force in y, but wait, there is yet another force to be included. The other force to be included is basically the equivalent force, the equivalent nodal force. Now this is very important. Check out how to deal with distributed loads in the video I will show you above. This is how you deal with distributed forces. You calculate the equivalent nodal force. Now in this case it's WL over 2, so it's 5. Moment at 3 is, well, there is no external moment, 0, but wait, there is moment from the external distributed force. I think it was WL square over 12, I forgot. I totally forgot what it is. Let me just cheat very quickly. Yeah, I think it's WL square over 12, so it's negative 0.833. And at node number 4, you have F4y, which you don't know, and M4. Now, What about your displacement? Your displacement vector equals like this. I've done this before, so I'm just repeating very quickly. At 1, you have 0, 0. At 2, you have 0 for y and a theta, because you don't know what the theta is. And so theta 2. At 3, you have a deflection at 3, v3, and you have the rotation at 3, but this time you have the rotation only of one side. And the side you have the rotation of is the side that you are using in a regular fashion. And that's the reason why you can only release one side. Because if you release both, then your theta 3 would be 0. That's impossible, because practically speaking, there is a theta 3. But also practically speaking, there are two theta 3s. So you cannot say both are 0, or you cannot just condense or remove both of theta 3s. So at least one theta 3 must survive to be able to solve this problem. And the theta 3 that survives is the theta 3 from the element that does not get the special treatment. Element number 2 got the special treatment. Element number 3 has got the regular treatment. So the theta you get here is the theta of element number 3, actually. Of course, 0, 0 for element number 4. With that being said, you can dash and slash all those columns and whatever. And of course, what remains is going to be basically extracted. And of course, you have, I think you have the last two elements or something, like you have those two things to be deleted and those two things to be deleted. So the surviving ones are like 5, minus 3, 0, and so on. So I can see those survivings here, 5, minus 3, 0, and so on. With that being said, you can basically calculate and find the deflections. Here is a quick note that this force is basically from the distributed force. I've explained that. And this is from the distributed force. I also explained that. With that being said, you have what the problem requires you. You have the deflection at node number 3, rotation at node number 2, and theta at node number 3. But wait, this theta at node number 3 is the theta of element 3, because element 3 got no special treatment. How can you find theta 3 for element number 2? By using a regular stiffness matrix for element number 2 and giving a special treatment for element number 3. Like if you here use a special stiffness matrix for element number 3 and regular stiffness matrix for element number 2, then theta 3 that you get here is going to be theta 3 of element number 2. So that's the solution of this example. But wait, I told you that I wanted to talk about how the softwares deal with those releases programmatically. To do that, I want to use a white screen here very quickly. If you have an element between node number 1, node number 2, and node number 3, okay? This is element number 1, and this is element number 2. Now, in Strado, my structural analysis software, as well as in Robot, I'm not really 100% sure, but I have seen signs that suggest that. In Strado and in Robot, what happens is, if you don't release anything, then, well, this is element number 1 and this is element number 2. Let's say that you have released element number 1 at the end, okay? What happens in the finite element background is that you have node number 1, node number 2, node number 2 dash, and node number 3. So you can see we have added a new node and a new element. And the element that was added here is rigid in all directions except the released ones. Like if you release this element around the rotation around Z, for example, then this element would have a rigid stiffness, a high value, for all the directions except the release direction. And this is really good, and the reason why I'm saying that Robot has it is because in Autodesk Robot, when you release something, you have the ability to release something and provide something we call I think it was called elastic spring or spring, a stiffness. Like in Robot, you are able to click on release and provide a rotational or linear stiffness for this release. Now you can see that this rotational stiffness will be used to apply this for this element. And this is how softwares do it. In other words, softwares trick you by saying, well, this is node number 1, node number 2, element number 1, and they add an extra node for the release, and then they add node number 3. This is element number 3, and this is special element number 2, not through, element number 2, and this is special element number 3, which contains a special stiffness matrix where everything has high values with exception to what you release. What you release is going to have a 0.001 stiffness value. Of course, I know that my Master of Science and PhD viewers are now face palming because they know that having a small stiffness value would have two effects. Effect number 1, it would introduce error because the stiffness matrix will cause some imbalances in your energy state, because this little stiffness will basically require some energy to rotate. And 2, it would introduce no mode shapes because you are applying artificial stiffness here. And 3, it even worst case scenario could cause numerical instabilities or in the conditional number. This is really high level stuff, I know. Because of a small stiffness value, just besides a huge stiffness value of 1 million, this would cause numerical problems and issues, and we can solve them partially by using something called preconditioning algorithms and even solution algorithms like the skyline. Now, this is really high-level stuff. I tell you, like I know this because I have done this, and well, let's see the high-level stuff. So that's how softwares perform internal releases. And that's everything I wanted to talk about today. Of course, in this video, in this example, he didn't ask you to draw the moment diagram. If you want to draw the moment diagram, there is a video linked above that explains to you how you do that. And well, that's everything I wanted to talk about. With that being said, before I finish, I want to give a huge CE-sized shout out to our dear channel members whose name are going to be shown on the screen. I want to thank them from the bottom of my heart, as their contribution to the channel helps us deliver the stuff and the videos you want to deliver on time and with the quality that we want. And with that, I am forever thankful. With that being said, I hope that you enjoyed the video and that it was beneficial for you. Of course, if you have enjoyed the video, then please like, share, comment, and subscribe, especially subscribing, because it helps increase the reach of my channel. As per usual, this is the Civil Engineering Essentials channel, and we will catch you in the next video.